is from the National Laboratory of Scientific Computation. Professor Novotny is an expert in topological derivatives. And please, André.
Okay, thank you very much for the introduction. In particular, I will talk about topological derivatives. So, firstly, I would like to thank the organizers for inviting me, in particular, Marcelo, Elcio, and Antonio. I am really happy to be here in this nice meeting. So, I will present a reconstruction method for a class of inverse problems based on the topological derivative. The outline of my presentation is the following. I will introduce some motivation. Then I will define the topological derivative. Then through a simple example, I will try to convince you that it's a good idea to make holes. Then I will talk about some applications of the topological derivative. And then I will introduce the second order topological derivative concept, which is crucial for the main part of my talk concerning the EIT problem. Okay, which is here is I introduce this example as a toy problem to fix the ideas. Okay. So the general framework is the following. We have a shape functional psi, which depends on geometric domain omega. And then we would like to minimize this shape functional with respect to omega, which belongs to a set of admissible domains. So the idea is the following. We have the original domain, and we would like to find the optimal domain by changing its shape and topology in order to reach some extreme of this functional. Since I am talking about change of topology and shape, our very general approach to this kind of problem is based on the topological derivative concept. It was introduced some less than 20 years ago by Jan Sokolovsky and Antoni Sokolowski in 1999. And the base idea is the following. Given the original domain omega, we will choose some arbitrary point of omega denoted by x hat, and the idea is to introduce some singular perturbation at this point. Here, in the example, we have a hole. This hole is denoted by small omega. Epsilon is the small parameter governing the size of this singular perturbation. Okay. So we have now we have a new domain which depends on the small parameter and on the position x hat, which is given by, in the case of holes, is given by omega minus the closure of small omega epsilon. And then we are interested in this expansion. I mean, we have the shape function associated to the perturbed domain, which is approximated by the shape function associated to the unperturbed domain plus some correction factor plus a remaining. Here, f epsilon goes to 0 when epsilon goes to 0. And then based on, this is the remaining, so based on these ansatz, we can define the topological derivative. The topological derivative is written as this object tau of x hat, which is given by this limit. So since we are past the limited epsilon going to 0, the topological derivative is defined through quantities associated to the original domain as any derivative. However, here we are dealing with sensitivity analysis with respect to sets because the unknown here is geometric domain. And we can deal with singular perturbations, like holes. Okay, so omega epsilon and omega have not the same topology. So in order to compute this limit, we have to use some tools from asymptotic analysis. This is the main ingredient. Okay. However, once we know this quantity, tau of the x hat, we can use it as a steepest descent direction in any optimization algorithm. In particular, let's suppose we want to minimize this shape functional, and suppose that f epsilon is a positive quantity. So we have to look for the most negative points of the topological derivative. If we enucleate holes where the topological derivative is negative, then we can minimize the shape functional. So the idea is quite simple. Okay. Let me show a very, very simple example in order to fix the idea. It concerns a control problem with respect to a geometrical domain. Here, the control is given by a disk. Omega is a disk of unity radius. U is the state solution to this PD, and zeta d is the target. So in this simple example, the optimal domain is given by a ring. And the target, we take U solution to this PD restrict to omega star. So assuming that this has a radial solution, then this is the profile of the solution U. Here is the radius, the center of the disk. And the target is this gray region restrict to the restriction of U to the ring. So we can prove that the disk, the full disk, is a local optimizer of this problem. However, if we compute the topological derivative, we get this profile. And the topological derivative is saying that we have to make holes in the center of the disk. In particular, if we take the threshold of the topological derivative where it is negative, and we make a hole, then we get the optimal solution in one step. So it allows us to change the topology, and then in this simple example, we can prove that this is the global optimum. Okay? So this is the motivation why we are looking for this topological derivative. So for obvious reasons, it has many applications in topology optimization, inverse problems, multi-scale material design, image processing, fracture modeling, and so on. So here the list is not complete at all, but it's representative of the pioneers on the subject. Let me just highlight Jan Sokolovsky and Samuel Mistutz, for example. They are pioneers on this. So, but we can go further on the expansion by using the same idea. So now we have this ansatz, and we add one more term on the expansion. And the assumption is that buff f epsilon f2 goes to 0 monotonically with epsilon, and f2 has a high order on epsilon with respect to f. And then this is the remaining. So based on these assumptions, if we divide by f epsilon and take the limit, we get the first order topological derivative as before. And if we divide by F2 epsilon and pass the limit, we get what we called second order topological derivative. Okay? And then I will show some application of these ideas in inverse problems. Okay? In particular, as a model problem, as I told before, I choose the EIT problem, but of course it's not restricted to this kind of problem. But it fits the framework in the sense that the idea is the following. Given a geometrical domain, we have some inclusions, some anomalies hiding inside this domain. So we have no access to this anomaly, but we can measure something on the boundary. In IT, we have some electrical flux traveling on omega, and we have some boundary measurements of the associated potential, electric potential on the boundary. And from this information, we want to reconstruct the set of anomalies. In particular, in this setting, we have the domain omega with some hidden inclusion denoted by omega star, which is our unknown. Here, the boundary of omega is divided into two parts, one hidden boundary denoted by gamma and a visible part denoted by gamma m, where we have some measurement. Okay. And then from this partial boundary measurement, we want to reconstruct the set of anomaly. This is the main idea. So this problem is written in the form of an overdetermined PDE. Here, the unknown is the coefficient k omega star, which appears here in the main part of the differential operator. Zeta is some state representing the phenomenon inside the body. And capital U and capital Q are the Cauchy data. Okay, this pair of data is known. We assume that we know. In particular, we apply electrical flux Q, and we are able to measure the answer of the body with respect to this excitation. It's called capital U is the electrical potential on the boundary. Restrict to gamma m, a small part of the boundary. And by assumption, we assume that k omega star is piecewise constant function. Okay, so k omega star is equal to gamma on small omega star and 1 on the complement. Okay, so we have some jumps, some transmission condition which is not written here because we can understand this formulation in the weak sense. Okay. So this problem is clear difficult because it's an overdetermined PDE and ill-posed. And there is also a lack of uniqueness if the contrast gamma and the geometrical support of the inclusions or the anomalies are unknown simultaneously. This can be verified through a simple counterexample. For example, if we have a small inclusion with a high contrast, it can produce the same Cauchy data, the same trace and normal trace on the boundary as a bigger inclusion with a small contrast. Okay, so we assume that gamma is known, the contrast is known. I mean, the paradigm here is the following. We know what we are looking for, but we don't know where they are. Okay? So of course, this is the most difficult version of the problem. For example, if you know omega star and we want to find gamma, this is a parametric problem. It seems to be trivial. However, if we know gamma and we have to find the topology of the geometric support of the anomaly, it's a big deal. Okay, it's quite a difficult problem. So since we are looking for some geometrical domain, the support of the anomaly, so we can write this problem as a topology optimization problem. It means that we can minimize the misfit between the boundary data, the boundary measure on gamma m, and an auxiliary, and the solution to auxiliary problem U written this way. We have to minimize this quantity with respect to the set small omega. Okay? So U is the solution to this problem. Of course, Q must satisfy the compatibility condition, otherwise we don't have existential solution to this problem. And the uniqueness we get if we add this condition, provide that we know zeta on the boundary, the trace on the boundary. So this we can put here as a boundary data. So everything is okay, given k omega in this form. I mean, k omega is also a piecewise constant function. Gamma is known on small omega, and on the complement is equal to 1, as before. But here is any small omega. And is any small omega in such a way that we can take this guy empty. I mean, this setting, we don't care about initial guess. We can take anything. For example, empty. Okay, this is the main idea. So the method I am showing you, we don't need any initial guess. Okay. And then this setting, the idea now is to perturb the problem by introducing a number of ball-shaped anomaly, for example. So we have a number n of trial balls, let me say like that, with center at some arbitrary point xi and radius epsilon I. So we introduce a coefficient, piecewise constant coefficient in this way, where it's equal to gamma in the balls and 1 on the complement. Here, just to simplify the notation, this is actually a vector of radius and a vector of locations, epsilon xi. And then we have the perturbed shape functional, which depends on the small parameter through the solution to the state problem, the perturbed problem. Okay? And then from these elements, we can state this result, where the shape functional associated to the perturbed domain can be expanded asymptotically in this way, which is approximated by the shape function associated to the unperturbed domain. This term can be seen as the first order topological derivative. D is the topological derivative, which depends on the locations. And alpha is written in this way, where each component is given by the volume of each perturbation. In 2D, here is the case, 2D is epsilon square. It's the volume, it's the Lebesgue measure of the perturbation. And then here we have the second order topological derivative, because here is epsilon 4. It's alpha squared times some kind of Asian matrix in infinity dimension. Okay, some remaining. So U epsilon is solution to this perturbed problem. And then U0 is solution to the unperturbed problem for small omega equal to empty. So we get this Laplacian equation in this case. Okay. So some terms require explanation. D is the first order topological derivative written in this way, which each entry is given by this quantity, where U0 is solution to the original problem, zeta is the target, and these are auxiliary functions that I will just present you. I will not bore you with the derivation. This is quite long, quite technical, but it doesn't matter. The important is the idea behind. This is the entries of the Asian matrix. Again, we have U0, zeta, and some auxiliary function. The important thing to keep in mind is that these auxiliary functions are defined in the original problem, in the original domain omega, with no anomalies. It means that they are somehow universal. We solve these guys once, and then we can compute everything, except U0, which depends on the excitation. Okay? So the only problem which depends on the problem we are dealing with is U0. The remaining functions here are somehow universal. We compute only once and tabulate it. In particular, U tilde is solution to this problem. It has exactly the same structure as before. U tilde, double tilde is solution to this problem. U tilde AG is solution to this problem. This guy, there is double index AJ because it takes into account the interaction between inclusions. This is why we introduce a number of simultaneous inclusions, because there are interaction between them. Then we have to try to extract this information through the asymptotic analysis, and then we get this result. And J, H, J2, and so on are explicit solutions depending on the solution to the unperturbed domain U0 and U2 and so on. And this theta AJ, which appears here on the right-hand side of this PD, takes into account the distance between inclusions. Okay, it is somehow explicitly the interaction between inclusions here. So in particular, it's a mess to arrive at this result, organized in this way, that in such a way that we can compute. But once we get this result, we can solve the problem using very simple arguments. In particular, we have the expansion here. Okay, and then we would like to minimize this quantity with respect to the parameters of the problem, which are the locations and the size of the inclusions. So let's truncate the expansion and take a look on this part of the expansion. This we define in this way, which depends on the volume of the inclusions, the location, and the number of inclusions. Remember that small m is the number of inclusion, which is an unknown of the problem also. So if we take a look, we have a quadratic form with respect to alpha. And we can prove that this Asian matrix is positive definite, provided that J is different of I always. Okay, I mean, there is no intersection between inclusions. In this case, this is positive definite, so this is a strictly convex function. So if we minimize with respect to alpha, we land in this simple linear system to solve. The size of this linear system is m times m. M is the number of inclusions we are looking for. Okay. And then once we solve this system, the size becomes a function of the locations. And then if we come back to the expansion, we have this step of minimization process. I mean, we have the locations are the comes out from the minimum of this functional in the set of admissible locations. Here, capital X represents the set of admissible locations. So the price to pay here is that the first step is trivial. It's minimization of a convex, strictly convex function, quadratic function. However, this second step of is somehow trivial because it's just combinatorial search in the set of admissible location, but it can become the bottleneck of the method, of course. But after solving these two problems, two steps of minimization, trivial optimization problem, we get the solution. The optimal solution is the pair of location, optimal location, and optimal size. I mean, here we find the optimal location for each location, then the best location, alpha evaluate on the best location is the optimal size. Okay, this is the output of the algorithm. So let me just discuss a little bit the complexity of the resulting algorithm. It is approximated by this formula, where small n is the cardinality of the set of admissible locations, okay? And m is the number of trial balls. So if we plot this, we have this behavior. We note that, for example, the green graph means the cardinality equal to 400 points, and m is this, m is here. So if we have a very small m, the complexity, we are working this region, the complexity is more or less under control. And then in the other extreme, if m is of the same order of n, then the complexity again is under control. However, if we take, for example, m equal to n over 2, we have this issue. I mean, the complexity blows up, it's infeasible. Okay? This is the weak point of the drawback of the method. So in order to fix the idea, let me show a simple example. Again, into two dimensions. Here we have a synthetic IT problem, where we have here the green, the red electrode represents Q, capital Q. It means we have a pair of electrodes. One is of injection of electrical flux. The other one is to drain. Okay, so this has to be to have null mean on the boundary, of course. So once we excite the body with electrical flux coming in and this is drained to come out, Then the other electrodes is used to measure the electrical potential on the boundary. So the blue electrode represents capital U, the boundary measurement. So of course we can combine it to produce different measurements. This is the idea. In our synthetic problem, the boundary is divided in some small pieces like that, highlighted here in thick line. And then it represents the electrodes of injection, drain, and the electrodes of boundary measurement. So more specifically, we are dealing with some partial boundary measurement. Okay, it represents half part of the boundary is visible and half part of the boundary is hiding. Okay. So this is a real life experiment here. The interest in this problem is that it's non-invasive, so we can do in vivo specimen. In the case here, a baby. This is to control, for example, apnea on babies. Okay. This is the electrodes. We can see here there is an electrode of injection, another one to drain the electrical flux, and the other electrodes are used to measure the potential on the boundary. And from this information, we try to detect some anomaly or something like that. So in the numerics, here we have, for example, the target. The target, we have 3 anomalies. So the background is corrupted by some noise. So this is a very aggressive way to include noise, to corrupt the background. With 5% of noise, this is the result of the reconstruction. Okay. Remember that this is just one step. We minimize. There is 2 steps of optimization problem, which is completely deterministic. We find the optimal candidate of size of the anomalies. Then we run a combinatorial search on the set of admissible location to get the optimal location. The pair are the solution which I am plotting here. Okay. With no noise, the reconstruction is almost exact. So if we have more noise, for example, 10% of noise, the solution is still okay. And if we have 15% of noise, which seems to be a huge quantity because we can see some degradation even on the picture. And the result's not so bad. There's some discrepancy here on these 2 inclusions. The location of these 2, it's okay. This one, there is some deviation, but it's acceptable. With 20%, it's complete degradation. So this is more or less the bound of the method. So, for example, in the case the anomaly is not given by ball-shaped. For example, we have this funny shape here. It was a surprise for us that we can approximate this by a number of balls. Okay. So this, we became very happy with this because it seems we can use this information as initial guess for another more, how can I say, developed methodology like the one based on level set and so on. If you were understood, the key point of the level set method, for instance, is how to find a good initial guess. And then with this methodology, it seems we have a good initial guess for this method. And of course, it also works on 3D. There is no any constraint. Actually, the expansion is completely different, of course, because the expansion I show before through the theorem, it depends on many, many things. It depends on the operator, on the dimension, on the nature of the anomalies. If it's whole, it depends on the boundary condition of the holes. If it's inclusion, depends on the transmission condition and so on. The shape of the inclusion also, of course. So the expansion is different, but the idea is the same. We have some expansion explicitly given in terms of the parameter under interest, like size and center of the anomalies we are looking for. Then we minimize trivially with respect to this quantity. Okay. The question how to find this expansion is the big deal. It strongly depends on the problem. Okay. If it's nonlinear, there is just a few development on this direction. For elliptic problem, is more or less under control. For parabolic somehow, and for hyperbolic, for instance, there is a question of regularity. We don't know. It's really a serious subject of research, I think. So as conclusion, just to fix the idea, I have presented a non-iterative reconstruct method. Since it's non-iterative, so it's quite robust with respect to noise data. And free of any initial guess, this is, how can I say, a feature of the topological derivative. We don't need initial guess. And this problem in this set of admissible solution, it has existence of uniqueness of solution, but we don't have stability. So if our method is non-iterative, so we get somehow stability for free. Okay, there is no accumulation of error during the iterations. Okay. So it has been specifically designed for a class of inverse problem where the unknown is given by a set of anomalies. Of course, we have to apply the topological derivative concept. We must have some jumps on the coefficients. Otherwise, it's a classical Frechet derivative. Okay. It has applications in, for example, gravimetry, inverse potential problems, seismic obstacle reconstruction, and so on. This is just a small list of problems which we have already applied these ideas. And as I told before, the main drawback of the method is the combinatory nature of the algorithm. For example, if the number of trial balls is much less than the cardinality of the set of admissible locations denoted by n, the complexity is treatable provided that m is small. This is the case I have shown. 2 minutes. Okay. If m is small m is of the same order of n, the complexity remains treatable, provided that even if we assume that high value of m, for example, and in this case is completely invisible when m is smaller than n. For example, m equal to n over 2, but the complexity blows up provided that m is high. So this is really the bottleneck of the method. So for now on, we are thinking about how to use this feature of the algorithm to apply to different problems. Okay. So okay, thank you very much.